Alright, so this is the notes for the Farley that I have equation posted out on the Disney trip. So, a couple of things of vocabulary. From before we learned about solutions, we're going to talk about homogeneous mixtures. Solutions are made from two components, a solvent and a solute. Solvents tend to be the ones that are in greater quantity. Often doesn't think of them as a liquid. Solutes tend to be a smaller quantity. Tend to be solids, but it's not always the case. Like soda is a mixture of liquid and gas. Carbon dioxide, in that case, would be a solid. If something's dissolved in water, it's a special type of solution called aqueous solution. And we can have solutions that have ions in it. So anytime we dissolve an ionic compound, such as table salt, the ions that make up the sodium and the chloride separate to make negative ions, in this case oxygen or cyanide, from example here. And then positively charged ions are called cations, if you remember that. Cats have paws, cations are positive. And then we can use electrodes to measure solutions concentration of electrodes, of cations and ions. And they can also measure the flow of electrons. For vocabulary, we can talk about the concentrations of solutions in terms of what's called molarity. So if you've ever made Kool-Aid, sometimes Kool-Aid, throw an extra tablespoon of sugar in there, make it a little sweeter. We can quantify that in terms of molarity, and that's just the definition defined by moles of solute per liters of solution in a simple capital M. We usually put brackets around whatever it is that we're speaking of in terms of concentration, and then follow that by its concentration, as shown here by our brackets of sodium ions. This will tell us a solution that has a concentration of sodium ions to be 1.0 molar. So an example here, I have 1.5 moles of sodium chloride dissolved to make 250 milliliters of aqueous solution. I want to know the molarity of the solution. So I read through the problem. I figure out what the problem gives me. I have 1.5 moles of sodium chloride. And that would be our and then I have 250 milliliters, which is the volume of solution. Now, by definition, molarity has to be in terms of liters, the volume of liters. So we're just doing a quick dimensional analysis. There are 1,000 milliliters in 1 liter, so that's going to give us 0.250 liters. So to find the molarity, we're just going to write the equation M is equal to moles over liters. We're going to take our 1.5 moles over 0.250, and that's going to give us a molarity of 6M, or 6 moles per liter. Anytime we have a unit that's a fraction like that, it lends itself very nicely for converting. So we're going to eventually do this, these molarities to convert moles to liters, or moles to volumes, volumes to moles. So additivity, real quick, we're going to talk about what happens when we mix things together. Well, if we're mixing things together, their masses will sum together. So if I have a 2-gram sample and I mix a 3-gram sample with it, I'm going to end up with a 5-gram sample. However, with solutions, or volumes, they're not additive. Meaning, if I have 2 liters of solution and 3 liters of another solution, I mix them together, I don't necessarily end up with 5 liters. And the reason for that is simple. Different materials physically have different sizes. So I always think if I have a bucket of grapes and a bucket of oranges, I dump them, mix them together, and put them back in the buckets, I might not get 2 buckets worth of stuff, because in the space between the oranges, I can squeeze some grapes in there, so the overall volume would actually be less. So for molarity, it's not always safe to assume that volumes are additive. 2 volumes together don't make the sum of them actually be less. But for our purposes, we'll assume that they're additive unless we're told otherwise. The way we make these solutions very accurately is we use special types of glassware. One called a volumetric flask that is specific for different volumes. They make really small ones, 5 milliliter volumetric flasks, all the way up to, I guess, 2 or 3 milliliter volumetric flasks. And they look something like this. So this is a flask. This one, I believe, is a 250 milliliter flask. It's tough to see on there, but on the neck of this, there is a line etched in it. And that line represents exactly the volume that's listed on it. Like I said, according to that's like 100 milliliter flask. So that means exactly at this line right here, you have 1,000 milliliters of liquid. So if I wanted to make a solution of a known molarity, I would measure out the amount of mass of the solute, figure out how many moles that would be. Plop that into this volumetric flask, add some water, stir it around, and then add more water until the volume is exactly up to that spot there. And there I've got a solution for concentration I know with certainty. Alright, let's look at an example of using one of these molarity problems. So we've got nitric acid, HNO3. It's exhaustively used in the manufacture of fertilizer. A bottle containing 75 milliliters of nitric acid is labeled 6 molar. How many moles of HNO3 are in this bottle? So I usually like to make a shopping list. So the first thing I see, I have 75.0 milliliters. And that's going to be a bottle. I also have a concentration for big M for molarity. I find that that's going to be 6.0 big M. Now I want to know how many moles are in this solution. Now, I know that molarity is equal to moles per liter. My issue here is that is not in liters, so I've got to change it to liters. So I know I can do that quick division by 1,000. That's equal to 0.0750 liters. Since I'm trying to solve for moles, I usually like to do the algebra before I plug numbers in. So if I multiply each side by liters, I get molarity times liters equal to moles. And then my molarity was 6M. And my volume was 0.075 liters. So let's see, 6 times 0.075. Let's see, that's going to give us 150 times 3. 150 times 2 is going to give us 3, 4. It's going to give us 0.450 moles in this case. Alright, so that's one example of how we do one of those problems. Another example, a reaction needs 5 grams of HNO3. How many milliliters of 6 molar solution are required? So a problem like this, here I'm given a mass. And I want to know how many milliliters. So I'm asking for volume. And I'm also given a molarity. Well, in this case, I know molarity is moles over volume. I'm missing 2 things from that equation. However, with mass, I can easily convert this mass into moles. So let's see, the molar mass of this, that's going to give us 48. 48 plus 14 is going to give us 63. Plus 1 is going to give us 64.02 grams of HNO3 in 1 mole. So I'm just going to take my 5 divided by 64. 0.01. I'm sorry, by 64.02. And that's going to give us 0.078 moles. I really should think of one more sig fig. Alright, so that gives me my moles. And now I can use the equation. M is moles over liters. In this case, I'm looking for liters. Ultimately milliliters. I'm going to find liters first. So if I cross multiply and then divide each side by n, I end up with liters is moles over molarity. I'm going to take my 0.781 moles and divide that by 6 molarity, or molar and I end up with 0.0130 liters. But again, the problem asks us for milliliters, and that's going to be 13 milliliters. So 13.0 milliliters. So that would be another type of molarity problem. Here we got 10 milliliters of water added to the solution. What is the molarity of the resulting solution? Assume the volumes are additive. So here we've got to go back and look at our initial volume here. We're going to start with 75 milliliters, and we know its concentration is 6 molar. So this uses a form of an equation. M1 V1 is equal to M2 V2, where the concentration of one solution times its volume will equal to a concentration of that new solution if we've diluted it by adding some more in there. So my initial volume was 75 milliliters, and that concentration from a previous problem was 6 molar. I've added 10 milliliters to it, and we're assuming that the volume is additive. So 75 plus 10 is going to give us 85 milliliters. And if we think about this, we've added water to it, so we've actually diluted it. So our new molarity should be less than our original 6.0. So M1 V1 is equal to M2 V2. We're solving for M2, so we're going to divide each side by V2. So now M2 is equal to M1 V1 over V2. And now we're going to plug our numbers in. We've got 6 molar times 75 milliliters over 85 milliliters. Now you notice on this problem I did not convert to liters. And that's because when we're doing these M1 V1 problems, we don't need liters, because in this case, as long as our units for volume are the same, we're going to end up canceling. So 6 times 75, divide that by 85. And that's going to give us a molarity of 5.29. Yeah, and that's just what we predicted. We imagined now we diluted this, and our molarity, our concentration decreased. It's more watered down. All right, so interesting thing happens when I kind of alluded to it when dealing with ionic solutions. When we dissolve ionic solids, in this case magnesium chloride, it's going to dissociate, right? Associate means to come together. Dissociate means to split apart. Magnesium chloride ionic compounds, when they dissolve, if they are soluble, as noted by this AQ, they're going to split apart into the ions that make them up. Now, that 2 down here tells me that there's 2 chlorides. Both of those chlorides are going to go their separate ways to make 2 chloride ions. Now, this doesn't follow the Brinkelhoff rules. It's only if we were talking about the element. In this case, we're dealing with ions. So the concentration of those ions are related to each other from the formula of the compound. So in this case, the molarity of MgCl2 would be equal to the molarity of the Mg, because there's a 1-to-1 ratio here. However, the molarity of the chlorine would be twice the molarity of magnesium chloride, right? We've got a 1-to-2 ratio here. And the total number of ions per unit of magnesium chloride to dissolve would be 3. I've got 1 magnesium ion and 2 chloride ions for every magnesium chloride formula unit that gets put into there. So this is a good place to stop this screencast. We'll look at we'll pick up here on part 2.